There we go. Here we go. We're now recording again. We're going to knock this out. I will post due dates again online. I'm not going to repeat all that stuff. What I want to do is now dive into what I was intending to do. Okay, so we're going to start with the mole. The mole is a unit of measurement, and it's used for measuring really large numbers. Technically, the mole can be used for any object or thing. There can be a mole of anything. Okay? You could say 1 mole of people, 1 mole of cell phones, 1 mole of elephants, 1 mole of stars in the sky. It doesn't actually apply to necessarily anything specific. Now, yes, the idea of mole, as far as the origination of the actual unit, you could say was from the word molecule. I'll just pretend that that's true. Whether or not it's true, I'm not going to tell you. There was a gentleman by the name of Avogadro who came up with the idea. He originated the idea of the mole unit. He didn't actually calculate an accurate number in 1 mole, but he came up with the idea of it. His idea is that the number of particles, be it an atom or a molecule, or a formula unit of an ionic compound, is equal to a certain number. Now, it goes a little bit more beyond that. Okay? What it really is, for example, the number of atoms in a mass equal in magnitude to the atomic mass of an atom. We'll start with atoms. Okay, so the number of atoms in a mass equal in magnitude to the atomic mass of an atom will contain 6.022 times 10 to the 23rd atoms. Now, his idea was just that they would always be the same. He didn't come up with 6.022 times 10 to the 23rd. He said that if you have 1 mole of potassium and you have a mole of sodium, then it will always contain exactly the same number of particles. It'll always be 1 mole will always be 6.022 times 10 to the 23rd atoms of potassium, or 1 mole of sodium will contain 6.022 times 10 to the 23rd atoms of sodium, and the mass of that will be something very specific. Okay. Now, there's different ways of explaining this, different ways of thinking about this. So what we're saying is 1 mole is always 6.022 times 10 to the 23rd things that we're talking about, okay? And 1 mole of hydrogen, which has a atomic mass equal to, let's say, 1.008 AMU, we'll have what we call a molar mass of 1.008 grams per mole, which means the mass of 6.022 times 10 to the 23rd atoms of hydrogen is 1.008 grams. Okay. 1 mole of hydrogen will contain 6.022 times 10 to the 23rd atoms of hydrogen, and 1 mole of hydrogen will have a mass of 1.008 grams. Okay. I'm going to look at this in a few different ways because the mole is an important concept, and I don't want to spend tons of time on this because that's what reading is for. That's what online lectures for. But I do want to explain this at least a little bit. This is an important concept. This is something you're going to have to work with. Okay. Any questions about this? Okay. So what this means is what you can do is you can actually utilize this to find this thing called the molar mass. And the molar mass is number of grams per 1 mole of pure substance. And the molar mass is a conversion factor allowing you to convert from mass in grams to moles and back again. You can convert with the molar mass to moles. Once you know moles, you can use that, and then you can convert from moles back to grams. Okay. You're going to need to practice this. This will be very important, et cetera, et cetera. You'll need to be able to do this for this lab. Okay, so very quickly, example. C6H12O6. I always return to C6H12O6 because C6H12O6 is a hexose. It is glucose. It is one of the central biological molecules. Glucose, sugar. It is something that most organisms make use of on the planet. Let's start by saying that the atomic mass is easy to calculate because you can do that. Everyone should know how to calculate an atomic mass of a molecule because it is very simple to do. You go 6 number of carbons, so 6 carbon atoms times 12.01 AMU per carbon atom plus 12 H atoms times 1.008 AMU per H atom plus 6 oxygen atoms times 16.00 AMU per oxygen atom. Yes, I've done these calculations way too many times. This value, I even know, this is approximately 180 AMU. I'm just rounding it off. I'm going to stick with 180 AMU. I've done it so many times, I know that. It's annoying. Okay, so that's 180 AMU. What that means is the molar mass, 1 AMU is equal to 1 gram per mole of stuff. So that means the molar mass of C6H12O6 is equal to 180 grams of C6H12O6 per mole of C6H12O6. Okay. You guys following me? Is this making any sense? Okay. This is how I'm able to find the molar mass, because 1 AMU is equal to 1 gram per mole. It's just a one-to-one conversion, which allows me to go from AMU in the atomic mass in AMU down to the molar mass in grams per mole. Okay, it's just a one-to-one conversion. Good so far? Okay. With that in mind, then, if someone asks you, I've got something like 360 grams of C6H12O6, how many moles do I have? You'd go 360 grams C6H12O6, multiply that by 1 mole of C6H12O6, and yes, you can ignore the E if you absolutely want to 180 grams of C6H12O6. You can see that grams of C6H12O6 cancel. Then it's 360 divided by 180, giving me 2 moles of C6H12O6. Okay, good so far? Just track it all for you guys. This is just unit conversions. I've introduced new units, but this is essentially actually just math you've been doing since chapter 1. The only difference is I've introduced a new unit, I've told you how to calculate that unit and conversion factor, but there's nothing terribly new here, actually. It's just a new unit, and then how to find that conversion factor to get that unit. Okay? So that means if you're struggling with this, return to chapter 1 and review conversion factors. Okay? If you're struggling with this, review conversion factors. Okay. If someone asks, how many molecules of C6H12O6 in 540 grams of C6H12O6, well, what you do is you start out with 540 grams of C6H12O6. We need our molar mass again. You go 1 mole of C6H12O6 per 180 grams of H12O6. And now we return to Avogadro's number. 6.022 times 10 to the 23rd. In this case, it's molecules of C6H12O6 over 1 mole of C6H12O6. Plug all of this into your calculator and get your answer. Essentially, it's going to be 3 times 6.022 times 10 to the 23rd, somewhere on the order of roughly 18.066 times 10 to the 23rd is roughly the number you're going to get. Okay. Any questions? Yes. You're getting 1.8066 times 10 to the 24th. Yeah. I just was lazy and didn't move the decimal to give you the scientific notation. Yeah. Or not lazy, but just expedited things. Yes. Unless the question asks for it in scientific notation, or if the answer in the multiple choice is in scientific notation, you don't need to worry about it. But if the answer you get is 18.066 times 10 to the 23rd and you don't see it on there, but you see 1.8066 times 10 to the 24th, you should be able to recognize it. Does that make sense? Okay. Now, I don't usually try to play games on you guys like that, but you never know when you get tired. Good so far? Okay. If nothing else, I'm hoping this is at least preparing you a little bit for chapter 6. Okay? Now, that is some simple calculations. Do you guys remember balancing equations? I think we just did that last week. In fact, I think there might be an assignment due today about this very topic. Perhaps. How are you guys doing on balancing equations? Getting there? Starting to make sense? I'm hoping that in general, a little bit more practice balancing equations will become one of the easier things for you guys to do. Okay, I'm hoping. That's my hope. Practice, practice, practice if you need to. Okay. Now, coefficients of balanced equations are used to make mole to mole conversion factors. There's this whole not long-winded, this great explanation that you'll find in books and in videos that say you can't throw mass to mass and use those things to actually work out calculations in chemistry. And the reason for that is the mass of one atom of hydrogen is different from the mass of one atom of carbon, even AMU. The mass of a single atom of hydrogen is 1.008 AMU. The mass of one atom of carbon is 12.01 AMU. So you can't use mass-to-mass conversions. They're not the same thing. Okay? Same things when we're using molar mass of one atom or one molecule, you'll find that O2 has a molar mass of 32 grams per mole versus CO2 has one of 44 grams per mole. You can't use the mass is not the same thing, so therefore the mass cannot be used to directly measure equal quantities of these things. Okay? You can't use grams mass for direct chemical calculations, because a gram of oxygen does not contain the same number of particles as a gram of carbon dioxide. Okay? Watch. 1 gram of O2 times 1 mole of O2 over 32 grams of O2 times 6.02 times 10 to the 23rd molecules of O2 over 1 mole of O2 is not equal to 1 gram of CO2, because you're going to multiply that by 1 mole of CO2 over 44 grams of CO2, and then multiply that by 6.02 times 10 to the 23rd molecules of CO2 over 1 mole of CO2. And again, if you look carefully, it's these masses right here, mass in grams, that are going to mess with you and make sure that you do not have an equal number of particles. Okay? If you want to build a chair, you need 4 legs, a seat, and a back. Right? The ratio of these things is always the same. Just like if you want to have CH4 plus O2 and burn that, you'll get CO2 plus H2O. And the ratio of these things becomes a 2 there and a 2 there. So for every molecule of methane you want to use up, you need 2 molecules of oxygen. Why am I mentioning this? You can't look at this with regard to grams. You can't use mass here. You have to use particles. Okay? You need a molecule of CO2 and 2 molecules of O2. Just like you can't go, oh, I'm going to weigh out a bunch of wheels and a bunch of engines, and I'll use these equal masses of engines and wheels to build a car. Can you imagine the dysfunctionality of that effort to make a car? If you went 1 ton of wheels and 1 ton of an engine, or whatever, you get the idea. The engine's going to weigh much more than the wheels. So you're going to end up with something like 500 wheels to 1 engine. That's not a car. That's just a bad idea. Get what I'm saying, I hope? You have to have things in the right ratio, and you actually have to count things, not mass. Mass is not the same as counting things. Okay? All right. So if you have this equation CH4 plus 2O2 giving you CO2 plus 2H2O, this is an example of now a balanced equation. And what I was saying by mole to mole ratios, let's just say I have 5 moles of CH4. I can ask questions like, how many moles of O2 do I need to use up all of the 5 moles of CH4? I can ask that question, and knowing how to utilize a mole to mole ratio, you can actually answer that question. You can go 5 moles of CH4, and we know that there is a imaginary 1 here. Not imaginary. There is a 1 there. It's not imaginary. It's a 1. Now, we don't write in the 1 normally, but there's a 1 there. Okay? And there is a 2 here. And so therefore we can go 2, so multiply this by 2 moles of O2 over 1 mole of CH4. You can see CH4 cancels with CH4 right here, leaving us 10 moles of O2 are needed to utilize fully the 5 moles of CH4. If we want to consume all of the methane gas, the 5 moles of methane gas, we need 10 moles of oxygen gas. Okay? Make sense? That's what the balanced equation is telling us. Now, how many moles of carbon dioxide would be made from 5 moles of methane gas? If this makes sense to you, you could actually do that calculation in your head. Now, if you're struggling with that, that's okay. So, how many moles of CO2 and O2, H2O, sorry, not O2, H2O are made from 5 moles of CH4? Well, you look at your balanced equation, 5 moles CH4 times, it was 1 mole, see back here, it's 1 mole of CH4 to 1 mole of CO2, or 1 mole of CH4 to 2 moles of H2O. That's what this equation tells us. Okay? So we have ratios that give us 1 mole of CO2 to 1 mole of CH4 coming from the balanced equation. Units cancel, and you're left with 5 moles of CO2. The same thing can be done for water. 5 moles of CH4. You have 2 moles of H2O over 1 mole of CH4. Units cancel. 10 moles of H2O. Now, can you get the mass of the water? Of course you can. You calculate the molar mass, which is oxygen is 16 plus 2 times 1 is hydrogen. So the molar mass of water is 18 grams per mole. And then multiply 10 moles of water by 18 grams per mole, and you get 180 grams of water. Hopefully, this is starting to make sense. I hope. Okay. And my hope is that I inspire you by showing you guys how quickly I can do this stuff. My goal is that you could see me doing it relatively easily, and so you can go, okay, if he can do it while he's sleep lecturing, then it's not a problem. We can actually have the periodic table, have a calculator, and we can do this. You guys are allowed pen and paper. I'm not, and we go, and you guys have no problems. Okay. Does that make sense at all? Okay. If not, I don't have any more time to really do this. Let's just talk practicals now. Okay. So ionic compounds. Do not have a definite, defined, finite size of particle. If you buy sodium chloride, pure sodium chloride from the store, they don't say, here's 5 clumps of sodium chloride. They just give you, here's a container of sodium chloride. Okay. If you compare the cooking sodium chloride that you use, fine grain sodium chloride, and you compare it to the rock salt that they use on roads, yeah, the size of the crystal is different, but the composition does not cause that. That's just caused by people breaking bigger pieces of sodium chloride down. The only thing that determines the size of a sodium chloride particle are people. Sodium chloride doesn't care. It'll get as big as it can. Okay? So that's why we use the formula unit as a symbolic representation of truly ionic substances, because it is just the lowest common ratio of charge. That's for ionic compounds. Now, if we're not talking ionic compounds, and we're talking about things that might form covalent bonds at times, if you have covalent bond formation, remember, covalent bond formation means electrons are shared and not transferred the way they are with ions. Covalent bond formation means you have a molecule. Molecules are defined. They are finite. Always the same size. They are specific things. They are a specific substance. Glucose is C6H12O6. Methane is CH4. A single molecule of methane will always have the same chemical properties, the same chemical composition. Just like glucose will always have the same chemical properties, the same composition. That's what's different. You could throw sodium chloride is always going to be sodium chloride. But you can arrange a different number of carbon and hydrogen and oxygen, get a different molecule, and therefore that molecule will have different properties. Okay? You can have something like C2H2 compared to C2H4 compared to C2H6, and these are different things, and they will always occur in these ratios of atoms because these are molecules. They will always have very specific structures. This thing will always look like this. Here is its Lewis structure as the structure now. No longer the symbolic representation, but the actual structure. Here is this guy, the structure. And the structure of this thing looks like this. And these are three very different molecules with different properties, different boiling points, different mass, different molar mass. Okay. Molar mass of this first one is going to be 26. Then you've got 28. Then you got 30. Very different molar masses, always the same. Okay. And they're just composed of carbon and hydrogen, but they're discrete particles. Good so far? Okay. Let's then talk about the molecular formula. The molecular formula is the precise molecular composition of a molecule. tells you the total number of atoms of each element in the molecule. Okay. Now I'm saying it's the total number because we have a different term, and that different term is the empirical formula. And I'm only mentioning this because the empirical formula shows up in this lab. So I don't want you guys to be lost. I want you to have the definitions. Okay. The empirical formula is the lowest common ratio, I should say, most reduced ratio of elements in a molecule. It does not tell you the full composition. It just tells you the ratio of elements to each other. Maintains the ratio, doesn't tell you the total. Okay. Now, why is this important? I'll show you guys in a second. Now, can you see the difference between these two things? The empirical formula is a most reduced ratio of elements in a molecule, versus the molecular formula is the total number of each element. Okay, the top one will show you the difference between different molecules that have the same ratio, versus the bottom one. You can have a whole bunch of different molecules that have the same ratio, and if you have just the empirical formula, there's no way to tell them apart because it's just telling you the ratio of elements that's been reduced. Okay, example. In general, have you guys ever heard of carbohydrates? Anyone never heard of carbohydrates? You guys have heard of carbohydrates, right? You know why they're called carbohydrates? I'm about to show you why. And this comes from the empirical formula. The name, not Maine, these are not lions. The name carbohydrate, one place it comes from, the empirical formula. For all carbohydrates, which is essentially the same. That's oversimplifying, but in general, the carbohydrate empirical formula is CH2O, carbohydrate, carbo water, carbohydrate. Let's look at the molecular formulas. For pentoses, hexoses, in general, pentoses are C5H10O5, which returns you to that ratio of CH2O. All I've done is multiply CH2O by 5. Hexoses are C6H12O6. A hexose is glucose or fructose. They are all hexoses. Pentoses include things like ribose, ribulose. Those are deoxyribose. Those are all pentoses. C5H10O5 is their molecular formula. These can all be re-reduced to the empirical formula for carbohydrates, that is CH2O. H2O. Okay, does that make sense at all? So the empirical formula just tells you the most reduced ratio of elements within any group of molecules, but doesn't tell you necessarily what the molecule is. The molecular formula tells you exactly what that molecule is. Is it a pentose that has 5 carbons? Is it a hexose that has 6 carbons? And it maintains that ratio, C5H10O5 or C6H12O6. Okay. Hopefully that makes a little more sense now. That's what I'm trying to convey here. Empirical formula is a reduced ratio. The molecular formula is the actual composition. Okay. So, stoichiometric equation, empirical formula, molecular weight, or the molar mass, the formula weight, the mole, Avogadro's number. Those are the key words on that first page. We've talked about a bunch of those. Let's see, blah, blah, blah. So, how do you calculate an empirical formula? Well, starting on page 85, they start telling you how to calculate an empirical formula. Okay. How do you calculate an empirical formula? What you do is you'd actually start with that. Okay, so if we had N2 plus H2, and we had no idea what the product is going to be. We have no idea, and we happen to combine 28 grams of N2 to fully react. Now, this means to leave nothing behind. We managed to get 28 grams of N2 to react fully with 6 grams of H2. These are both gases. We do that. The first thing you need to do is find the number of moles of each atom. Okay. You need to know what are the moles of each atom that have been combined. So you go 28 grams of N2. Now, what's the molar mass of N2? It's going to be 1 mole. We're going to invert it, flip it. How many grams are there per 1 mole of N2? What's the atomic mass of N2? How many AMU is in 1 molecule of N2? Not quite. It's 28. 14.01 is the mass of 1 atom. N2 is 2 atoms. So you've got to double it to give you 28.02 grams of N2 to 1 mole of N2. Does that make sense, guys? Okay. Now, the last thing we need to do is say 1 mole of N2 contains how many moles of nitrogen atoms? Precisely, yes. So per 1 mole of N2, there are 2 moles of single nitrogen atoms, like so. Okay, does that make sense? 1 N2 contains a nitrogen and a nitrogen, so that's 2 moles of nitrogen atoms. Okay, you do that, you go through, and you'll end up with 2 moles of nitrogen. Okay, they do it a little bit different on here. I know. I want to go all the way to the atoms. Okay, good so far? You guys follow me so far? Any questions? Okay. Then the next thing is, let's see, what is it? Find the number of moles of each atom. Okay. So then we've got 6 grams of H2. What is the, so it's 1 mole of H2. How many grams of H2? And you can just round it if you want to. You can round it to the nearest whole gram. I will accept that. Okay. Especially if it's, because what it is it's, the atomic mass is 1.008 AMU for 1 H atom. So you can just round that to 2 because it's very close to 2. Okay. So 2 grams of H2. Why 2? Because it's 1.008 times 2 because there's 2 atoms within a single H2 molecule. Okay. Make sense? Finally, it should be actually, sorry, 1 mole of H2 contains 2 moles of H atoms. Just like we did with nitrogen. 1 mole of H2 molecules contains 2 moles of H atoms. You go through and do this. Well, the 2's cancel. And you end up with 6 moles of H atoms. Okay? So we know right now that we've got 6 moles of H atoms and how many nitrogen atoms? Sorry? 2. Okay, perfect. 2 moles of nitrogen atoms. Okay? So the last question we ask ourselves, or the second question we ask ourselves is, what is the most reduced ratio of nitrogen to hydrogen in our mystery product? Exactly. It's 1 to 3. You go nitrogen to hydrogen is equal to 2 over 6, which is a ratio of 1 to 3, which means your empirical formula is nitrogen 1, hydrogen 3. Exactly. And that's how you find the empirical formula. You need to find the subscript whole number of atoms. That's what we just did. Make sense? That's what we're going to do tonight. Okay. Let's get started. All right. Let's look briefly. Sorry. Let's look briefly at what you're going to do. Okay. So what you're going to do is on page 89. You're going to weigh the crucible and its cover. You're going to cut a 25-centimeter strip of magnesium ribbon, and they should be already pre-cut in the back anyway.